This is part 2 of the video. This is for equation of lines and planes. We're going to look at an example here. So we need to find parametric equations for the line through 1, 0, negative 1, parallel to this line. And we need to find an equation of a plane. First, we'll find the parametric equations for the line. So we'll notice that we're given 1/3 x minus 4, etc. We're going to rewrite that as x minus 4 over 3, which is equal to y over 2, which is equal to z minus a negative 2 over 1. Now why we do that is that this is in symmetric equation form, and we could see the direction numbers, which is essentially gives us a rough idea of the slope of these of this line here is going to be used in the parametric equation. So we have 3 parametric equations. Where x0, y0, z0 is given right here. So we plug them in. And that's our parametric equations for the line. We use these direction numbers because it's parallel to, right? In particular, okay, because we have 3, 2, 1. Those are the same direction numbers that we're using here, because we know that in general parallel lines have the same slope. Here, parallel lines have constant multiple of the direction numbers. Let's look at the next problem. Find the equation of the plane. So here we want to find the equation of plane through these points here. First thing you need to do is you need to call, we'll just call this point P, this point Q, and this point R. Then what we're going to do is we're going to find what the vector PQ looks like in component form. So we have 4 minus 3, 0 minus a negative 1, 2 minus 1. So PQ in component form will be 1, 1, 1. And we do the same thing, but instead we're doing PR. So we have 6 minus 3, 3 minus a negative 1, and 1 minus 1. So we just compute that, 3, 4, 0. We found 2 of these factors in component form, and what we'll need to do is we'll need to find the orthogonal vector, normal vector, to these 2 vectors. So that we're going to have to use a determinant, 3 by 3 determinant. So we'll just call this n, and we set up our determinant using the component vectors as the row vectors. And let's compute this 3 by 3 determinant. So we have 0 minus 4I minus 0 minus 3j plus 4 minus 3k. We'll simplify that. Negative 4I plus 3j plus k. And that's our normal vector n. So when we have that normal vector n, we just want to use these as the direction numbers and use the general equation of a plane. And we choose our point, one of our points here, to go through. So for what we have here, we can rewrite this as x minus x0 equals b, y minus y0 equals c, c minus z0, where these are the direction numbers a, b, and c. So we have negative 4x minus, I'm going to just choose 3, negative 1, 1. So x minus 3. And the second one is going to be 3, y plus 1. And for the last one's going to be 1, z minus 1. That's the equation of our plane. So that's how we would do it here. Notice that the n, right? N is just a normal vector, or you could say that's the orthogonal vector to these two vectors here. And this is basically like taking the cross product, right? P, Q, PR. If you take the cross product, this is what this is, and you get an orthogonal vector to both PQ and PR. And we use this orthogonal vector to find the direction numbers for the plane. Surfaces. So there are a whole bunch of surfaces here that we can go through. A lot of these are in your textbook, a lot of pretty diagrams. Not going to copy and paste all the diagrams here, but I'm just going to give you a general idea of graphing in 3D space. So identify and sketch a graph of each surface. X equals 3, y equals z squared, etc. Okay. So the first couple we can do pretty quickly. So like for A, just draw your 3D plane. And typically we call this X and Y, although some people might, determine something else. And here we can choose direction, so we just choose this to be positive here. So X equals 3. So X is always 3. Y can be anything. So it's just a line on this plane here. Okay, so X equals 3 just looks like this. This is just in the 2D plane. If you think of like XY, this is a Cartesian plane, and if we invert that, you could just see that's just a vertical line. On the XY Cartesian plane, R2 and R3, it just looks like a flat line going across. So that's that's how we can interpret that in terms of R3. Y equals z squared. I think we can probably already know what this is going to look like a bit. Forgive me if my drawing is not that great here. In the YZ plane, okay, it's just going to look like a parabola. Now, if you want to get a couple coordinate pairs, you could certainly do that. When z, when z is 1, y is 1, for example. When z is negative 1, y is 1. So you can kind of see what this is going to look like. When z is 2, y is 4. So you can kind of connect the dots here and see when z is negative 2, then we get it's negative 4. I mean positive 4, sorry, positive 4, so it's over here. Forgive me for my drawing here, but anyway, you get this. This is in the YZ plane. It's just a parabola in the YZ plane. So something that we're pretty familiar with. Now for the last two, I'm going to go to the next slide. You're going to see here for the next two, we got 4x minus y plus 2z is 4. This is a plane where you want to take traces. So what is a trace? So a trace is when you hold one of these to be 0 and then leave the other two. So if I let x be 0, all right, I'm going to have a yz trace. This helps me get an idea what it looks like. Negative y plus 2z is 4. So I get 2z minus 4 is y, which is just a line. We could take usually there's 3 traces, obviously, because there's 3 coordinates, so you could take y equals 0. So I get the xz trace. So you get 4x plus 2z is 4, or 2x plus z is 2. And you could solve, if you want, you could solve for z here, or you could solve for x. It doesn't really make any difference. So that z is equal to 2 minus 2x, for example, which is also another line. And we could take finally a third trace. You could sketch these lines. That's the idea. X equals 0, z equals 0 rather. So we get the xy trace. Xy trace is 4x minus y is equal to 4. So we can just solve for y as negative y equals 4 minus 4x, or y is equal to 4x minus 4, which is a line. So we have a couple of lines here. We have a few lines that we can trace out, and then we get a plane. Now, most often we have 3D software to deal with this type of situation to use, but it's important to know the idea of a trace, how to compute a trace, how to just sketch what you're given, even though it might not be 100% nice to look at. Still, just to get an idea. here. So we have z, we have x. So we can start with this z equals 0, xy trace. So z is 0, which means we're on the xy plane. And when x is 0, you see y is -4. So let's just make this -4, x is 0. When x is 1, we see we get y is 0. And so on and so forth. We get a line over here, so we can keep on going. X is 2, for example. Then we get 4, y is 4. And we can keep on going. Now that's only for when z is 0, right? So, you know, z in reality can be any value, right? It could be any value, it could be 12 or whatever. So we have to keep that in mind when we're doing this trace, is that even though this line here is a line, this is only for when z is 0. Okay, let's go over here. When x is 0, we have 2z minus 4 is y. So let's let z be, I don't know, 0. So we get y is -4. So we get this point here. Let's let z be 1. So since z is 1, y is -2. It's supposed to be my -2 there. And when z is 2, y is 0. Okay. And let's do the last one. When x is 0, then z is 2. When x is 1, z is 0. And if x is 2, then z is -2. So this one kind of looks like it's coming out at us, although it's kind of maybe difficult to see. But anyway, we see we have a plane area right here. Okay. Now that plane area, we can that triangular region that's bounded by these traces is actually it is a triangular region, but it's only a trace, right? So the z could be anything. So that triangular region actually spreads throughout the entire plane. Okay, so in reality, it kind of looks like a big sheet with that same slope, has the same direction numbers. All right, so basically you'd have the plane would extend infinitely in each direction. So if I just take this 4x and the equation and look up 3D calculator GeoGebra on my Google, I can place this in. And we see we get a sheet here, okay, and that's the plane. And you could play around with this however you like, but that's what we get more or less. All right. You see it passes right through. Z is 2 here. And you see what x is 1. z is 0. And that triangular region that we found was bounded here, but we can extend that throughout the entire plane. Okay, so it can just go up and down that entire plane. So that's how we find that. I'll make another video for the last one. Thank you for watching.